Session 2, we will talk about the natural logarithm. Session 2, we will talk about natural logarithm. So when we talk about natural logarithm, normally we need to face this symbol, E. E, did you learn this constant before? No, right? Did you learn constant pi? Pi? 3.14. 15, then okay. Anyway, I also cannot memorize so many digits. E is also an irrational number, just like pi. It's an irrational number, just like pi. Pi, we know it is 1.14159, blah blah blah. Okay, E is 2.71828.459, blah 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 blah. Actually, it's hard for you to precisely pinpoint on the axis because it's an irrational number. So, but this constant is very important. Maybe when your future course you will take, you will always face this number, okay? But it is an irrational number, just like pi, okay? So right now, maybe in the past you already know this, but right now we will give it another definition to define this number. So we need to face the first definition related to this number. This is the natural logarithm function. We will define a natural logarithm function. It will be defined just like this, that ln, okay, x as its input, right? I define it as integral from 1 to x. The integrand is 1 over t dt. And x should be positive number. That's very important. Okay, so if you just follow this definition, actually it's easy to try to image the function number, because it's just like if the horizontal axis is t, then here is y. Then we will face this function, y is equal to 1 over t, right? 1 over t is integrate. So starting from 1 and ending at x, right? So if the start point 1 is here, this is the start point, right? And the end point is x, maybe here or maybe here, but x should be positive. Okay, so if x is larger than 1, actually the function number you can regard it as the area, under this curve above the x-axis. We are talking about its area, right? If you want to calculate this, it can be regarded as calculating the area under this curve from 1 to x. Did you remember when we just faced the integrand is a positive function? Actually, it can be regarded as calculating the area under this curve。当被积分的式子是一个正函数的时候，我们说它如果是一个正函数，代表什么函数都是正，对不对？如果我们在算它的积分等同于什么？那个函数在那个 x 轴以上的面积，对不对？我们当初讲积分有正有负，是因为它函数掉到负的，要跑到正的，这个时候积分就有正有负会去互相抵消。可是万一这个函数是正的时候，等同于它在算它的面积。So when you just face this, so we can just regard it as the curve, the area under this curve and above the x-axis, and try to calculate the area, right? Starting from 1 and ended at x. So if s is larger than 1, then we can find ln x is equal to integral 1 from x 1 over t dt. It should be positive or negative. If x is larger than 1, positive, right? It's quite obvious. It should be positive, right? But if s is equal to 1, as a result, ln x will be 0, right? Because it will be from 1 to 1, 1 over t dt, 0. Because you can see the start point and the end point are the same, right? So the area should be 0, right? And when we consider if s less than 1, of course, it is larger than 0, right? Then we can regard this 1 also ended at x, 1 over t dt. We can change the position from minus x to 1 over t dt, right? Because x is less than 1, so x should be here. From one number less than 1, 1. This part will be positive. Then with this negative, eventually the number should be less than 0, right? Less than 0. So through these three classification, you can see when s is larger than 1, the number should be positive. When s is equal to 1, the number ln x value should be 0. And finally, if s is less than 1, also positive number, the answer will be negative. So we have a rough estimation for ln x function value. Okay? So this is a very simple classify for these three parts. But later on, we will go into its function value for the in the future study. We will know that. Then we are talking about E, right? So we will define what is E. The constant value, the number E is the number satisfying ln E should be 1. What does it mean? So you can see as x is far away from 1, you can see the ln x value will keep going up, right? Will increase. So for example, in the beginning, if x is 1, then the number is 0. Maybe somewhere the number will be 0.2, somewhere will be 0.4, blah, blah, blah. when a spatial point E, for example, E may be here. The idea is if the total area is 1, if we find the area is 1, then we will stop. The place we stop is E. Can you imagine that? So actually, the number is around 2.718, blah, 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 blah. Okay, so if you want to find E, it's easy. You can just, actually not that easy because it's an irrational number. Actually, it's hard for you to pinpoint the exact location to identify where is E. But based on this definition, we will say, okay, please just tell me at which point, at which endpoint will make the area become 1. Can you understand that? Right? 我很快讲一下哈，就我们都知道大于1之后的 x， 它的面积的值就会越来越大哦。虽然它这个会往下降，对不对？但是再怎么说，它是一个递增的，因为越来越大，对不对？那 ln 它定义这个是怎么定义的？是说你就是从开始往右边走，走到哪一个点，让它的面积刚好等于此一非彼一了哈。这个是这个常数这个是 constant 的 1。如果这个面积是等于1的时候呢，中值点停在那里的就是1，那这个就是我们刚刚开始讲的，它约莫大概是2.7828 blah 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 这些哈，你是很难点出它真的在哪里的，跟派一样。Okay, so this is the basic concept. So since this is definition, so we just follow the rule. So you need to memorize that based on the natural logarithm function, the definition is just like this. And ln E should be 1. Okay? So please keep these two results in your mind. Then, okay, since this is a function, right? This is a function, right? Ln x is a function. It's f of x, right? So we can try to differentiate the ln x, right? So it will become, by following the definition, it will become this. So what is the result? Yellow. Okay. Yes, this part, right? So the answer will be 1 over x. Why? Why is 1 over x? Did you still remember the fundamental theorem? We just integrate something, then differentiate the result. Then we can get the result back. Did you remember? 微积分基本定理，先积2分，再微分，它会还原。But don't forget, t here is t. This is x. Okay? So please just memorize it that when you just differentiate ln x, the result is 1 over x. Please also keep the result in your mind. Okay? But basically, following the definition, you just follow the rule of calculus, fundamental calculus, fundamental rule, you can get the result back. So if y is equal to ln u, then u here normally, if you still remember, u will be denoted as a differentiable function. Of x, right? So that means sometimes in next semester normally we use u as blah blah blah, blah x, like cosine x, s squared plus 1 over x, sine x plus cotangent x, something like that. So anyway, u is blah 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 x, right? So when we differentiate it equal to the nu, what is the result? What is the result? Very, very similar to this result, but the difference is we need to use a rule, chain rule. Yes, correct, chain rule, right? So it will become d over du ln u, right? Then don't forget you need to have du over dx back, right? So based on chain rule, you can see, or based on the differential, here and here can be cancelled, right? Or chain rule, also follow the rule. Okay, so the answer will be this part will become 1 over u times du over dx. So in a special case, when u is equal to x, then you will get this result back, right? If u is x, then here is x, dx over dx will become 1, and then you can get the result back. So this result is more generic, right? It's more generic. So I will give you an example to show how to do that. That if we want to differentiate ln s squared plus 3. So see, u here is s squared plus 3. So based on the rule, you can see it will be 1 over u times du means differentiate s squared plus 3, right? So the answer will be 2s over s squared plus 3. So sometimes when you just see this result, you can just find that when I integrate this part, the result will be ln of s squared plus 3. But later we will talk about the integration. So, but I just want to give you a very rough imagination about the differentiation for ln x function, or ln u correctly, I should say it should be as ln u instead of ln x, right? Because ln x is a special case for ln u. A special u is equal to x, right? But in general, should u should be blah 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 x, right? So in general, it should be blah 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 x plus some constant, something like that. Okay. So is that okay so far? Okay. So then we will talk about its properties of logarithm. So the second theory is about for any number a here should be positive, okay? A should be positive, and x is also positive. Then we will talk about 4 properties. The first one is ln ax is equal to ln a plus ln x. The second rule is ln a over x will be ln a minus ln x. Then the third one is ln 1 over x, it will be minus ln x. Then the last one will be ln x to the power of r, it will be r times ln x. actually, these four properties, I believe you already learned that. In the past, maybe you just learn logarithm. So you just try to replace ln as log using 10 as a basis, then you can get a result, right? But in our class, we will introduce ln first. So we can regard ln x is using e as a base for the logarithm. But eventually we will introduce log for you based on the definition of ln x. But so far we will face this four rules. 你看看这四个有没有很在你以前中学有没有学？哎，你们有学过 log 对？有吧？啊 ，log 基本的，最基本的。你把这 ln 换成 log， 你会发现蛮像，非常像，基本上是同一个，但是只是它 base 不一样啊。But eventually we will face the normal log function instead just ln x. Okay. So, and even though there are four rules, four properties here, we can just focus on number one. Then for number 2 to 4, you can just derive the result based on number one. Yeah. So I will prove number one for you, and then you can gradually. We will just prove this one. Then based on this, you can get this one, and then you can get this one, and then you can get this one. Okay, I will show you the first one first. What I try to prove of number one. So I face ln ax, right? At the left hand side, I face this one. So I try to differentiate. What's the result? What's the result? So you can regard here is u, right? So based on we learned earlier here, we will have 1 over u du dx, right? So the result will be 1 over ax, correct? Then du dx, du u is here, right? Yeah. So that what's the result? It will be 1 over ax times what? A, yes, correct. So we can cancel it, then we can get 1 over x, right? Then we also know that dx differentiate ln x, the result is also, what's the result? ln x, when I just differentiate ln x, what's the result? 1 over x. Yeah, don't forget, we just follow this, right? When I differentiate ln x, I still get 1 over x. So you can see there are two functions. One is this one is this one, even though they are different, but they have the same differentiation result, right? So I'm not sure if you still remember, if these two functions have the same differential result, then in between the difference is just the original function. The difference between two original functions will be just a constant. Did you remember? Okay, maybe I just note it down. Maybe you already returned. Yes. So did you remember when we say, maybe I just note it here. if you forgot, you can just go back to the previous chapter that if f of s and g of s are the same, even though I don't know what f of s is, what g of s is, then I can get f of s and g of s. The difference in between is a constant, right? Then, so right now we know this function and this function, they have the same differentiation result. So that means ln ax should be equal to ln x plus some constant. Right? Based on this, you can see this one is differential result is 1 over x. This one also has the same result. So in between, the difference is just one constant. Right? So we can continue. If s is equal to 1, we can get ln a times 1 is equal to ln 1 plus c. Right? See, here s is 1. So 1 is put here, also put here. Then we can get ln of a times 1 is equal to ln 1 plus c. So ln, what is ln 1? 0. 0, right? So here should be 0. So we can get c is ln a. So we just replace the result back to here. So finally, we can get ln of ax is equal to ln x plus ln a. Okay? Is that okay? So for the rest part, you can also just regard this one. I can quickly give you a proof that about this. You can regard this as ln x times x times x blah 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 till x, and total I have r x here. So based on the rule, there are totally r ln x, right? Because you can just separate, right? Originally it's a multiplication, but when you just use ln function, you can make application, multiplication become addition, right? So finally, it's a result. So you can follow the similar rule to prove number 2 and number 3. Okay, I just proved number 1 for your reference. Okay, so far, let me just quickly give you a review about the result. That the first one is, remember, ln x should be follow this definition. Then when x is positive, is larger than 1, the result will be positive. S is equal to 1 will be 0. S less than 1, the total number will less than 0. Then the second thing is ln e should be 1 by definition. Then I also hope you can just memorize this result, that when you just differentiate ln x, the result is 1 over x. And also these 4 rules. Okay, so the next I will introduce you about the graph and the range of ln x and aspect x should be positive, right? So we already know some property about ln x, but we didn't really draw its graph. So when we want to know the graph, there are many rules can be applied, especially for using differentiation. We can know, is it an increasing function, is it a decreasing function? If you want to know if it is a concave up or concave down, we can use second order the differentiation, right? 我们可以用一次微分了解它的递增性、递减性，我们可以用二次微分来了解它的凹口朝上或朝下，对不对？好 ，OK. So based on this, we can try to differentiate it. It should be, what is the result? 1 over x, right? And x is positive, so the result is also positive. So did you remember when we just have the first derivative, we can identify this function should be increasing function, right? It's an increasing function, right? So that means even though right now we didn't know its figure, its trend, but based on the result from its first order differentiation, we know it will be an increasing function or it is a decreasing function, right? So this is the first order differentiation. Then we continue to differentiate it. So that means that will become this. The result will 1 minus 1 over s squared. The result will be, because this part is positive, right? Positive over positive, then I have a negative sign here, so the result will be negative, right? So based on this result, how we can know ln x is concave down, right? So right now we can start to image that the curve is increasing, but concave up, concave down. So let me just slightly show you that this is t, this is y. So originally we just follow y is equal to 1 over t to get the result, right? And the start point is 1, right? Did you still remember ln x is equal to calculating the area under this curve? Then we can get the result, right? So, but right now, we can continue to analyze it for the portion A. When we calculate ln 2 to the power of n, so it will be n times ln2. Then this will be larger than n times 1/2. Why can I say that? Why can I say ln2 is larger than 1/2? Because ln2 means I try to calculate 1 to 2, right? So supposedly this part will be ln2, right? But ln2 is larger than 1/2. Why? Because at this point, when I use 2 as the input for y is equal to 1 over t, the result will be 1/2, right? So you can see 1 times 1/2. This part is 1/2. So it is very obvious. The red part is larger than the yellow part. The red part is larger than yellow part, right? So that I can get the result n times ln2 to be larger than n times 1/2. So based on geometric result, we can get a result. So therefore, when n is increased to infinity, so that means it's almost equal to equivalent to s is approaching infinity. Actually, here is not a very serious proof, but we can roughly estimate that when n is increased to infinity, in the beginning it will be 1/2, 1/4, then 1/8, 1/16, 1/64. Even though it's a discrete point, but we can roughly estimate that as n is increased to infinity, and as here is also increased. It increased to infinity, then we can find ln 2 to the power, we are going to infinity. So that means ln x also going to infinity, positive infinity. So this is the A part. For the B part, we also can try to do this minus n. What is minus n? The first point will be 1/2. The second point is n is 2, 1/4. 1/2, 1/4, 1/8. Then as n is increased, we can estimate the result when x is approaching 0. So we can regard this as minus n times ln2. So I follow the previous rule, because it's the power, we can move it from here to here, right? Then the result will be less than minus n/2. So when n is increasing to infinity, then we can get ln 2 to the power of minus n will also increase to negative infinity. Why? Because you can see here will be less than minus times one positive number. So as n continuously increasing, then we can get the result we are approaching minus infinity. So that also means that is almost equivalent when s is approaching 0, right? You can see as n, you can look at here, as n is continuously increasing, you can find this number will continuously going down, right? 2的负 n 次方 n 越大，这整个值会怎么样？越小，甚至趋近于零，对不对？当它很大，一开始可能是1/2，再来就是1/4、1/8、16/1、6/4、1/8，n 越来越大，它就会越来越接近零。好， 我们利用这个来模拟这个 NGX 趋近理。So finally, you can see lnx also approaching minus infinity when x is less than 1. So based on these two results, you can find actually the function value will be, I will use another figure. The result will be like this. Here, you can see this figure, lnx. This figure, the green curve is lnx. It is an increasing function, concave down, right? Concave down. And as x is approaching 0, it will approach negative infinity. As s is increasing to positive infinity, we will go into positive infinity. And when lnx passing 1, the curve will pass 0. So finally, this is the y is equal to lnx. This is the lnx curve. So we can just have a short conclusion about this. The domain of lnx will be from 0, not including 0, right? 0 to positive infinity. Domain, right? Domain. And its range will be negative infinity to positive infinity. So that means we also can say that limit s is approaching positive infinity, lnx, it will be positive infinity. Likewise, that in the opposite, we can get this one is 0, sorry, 0. Approaching 0, it will going down and approaching negative infinity. So I hope you can just memorize it, and through this not a serious proof, you can know actually later this result. Okay, so let's take a 10 minutes break and then come back to the classroom. So right now we already have differentiating ln u is equal to 1 over u times du dx, right? We already know that, right? By chain rule, we can get the result, right? So right now, I just do that ln u is equal to 1 over u du dx. So I just integrate this. So since these two ones are the same, so when I take its integrate at the both sides, we still keep the equality, right? So this equation will be still be held, right? Then for the left hand side, you can see where I just integrate this, when I differentiate this, then integrate this, I can get ln u back, right? By fundamental theory. When I differentiate something, then I immediately integrate the result, then I can get this back, right? For the right hand side, I will regard this is a differential did you remember differential can be regarded as a variable, right? So we can cancel it. So for the right hand side, we can get 1 over u du will be ln u plus c. Don't forget, this is this is not a definite integral, right? This is not a definite because we can have a precise starting point and point here. So finally, we can get this result. Okay, so please just remember this. Then actually I can rewrite this as this is equal to ln u plus c. Actually, these two ones are the same. So if u is positive, then we can get this result. Because did you remember ln u? U here should be positive. So no doubt we should write it down as this one. If u is negative, then we can do the original will be, for this part, we can change it as d minus du. So u is negative. When we write negative u, that means this part is positive. But you just add negative here, right? So we can change it as du. Sorry. We can change as negative d minus u, right? So minus, so that we can get it back, right? So even though u is a negative, we can just slightly change it by adding negative here, so that we can get a positive number here. But since you add this one, we also need to add a negative back here, so it will still the same, right? But the result will become, since this positive, so the result will still ln minus u plus c. So based on these two results, we can get integral 1 over u is ln, taking the absolute value of u plus c. So we can use this, have a unified result. 我们可以用这个式子统一了这两个分开讨论的情况，对不对 ？u 不管是正的 u 或者是负的，这个式子就完全包含进来。不包括的。不包括的。你的sorry, I forgot du. Forgot. Yeah. Okay, so we can have a unified result by this expression to express these two conditions, especially for u positive, for u negative. Use this one, it's a unified one. And so the second result is integral. Did you still remember this? Did you still remember this? In the past, we just talked about when n is not equal to -1. The result is 1 over n plus 1 u to the power of n plus 1 plus c, right? Because in the past, if u is -1, then we will let here become 0. It's not an illegal expression, right? But right now we already have the result, so we can just separate. When n is equal to -1, we can get ln taking the absolute value of u plus c. So right now we already have all result for when you just integrate u to the power of n. And right now n, no matter n is equal to -1 or no matter n is not equal to -1, we can have the result. So the second thing for you, you should notice this one. 记得吗？我们在上学期的时候，这个我们是学过的。对，有没有？对于 u 的 n 次方的积分，对 u 积分的话，我们要往上提升，对不对？对。然后呢，为了这个系数下来，微分下来之后，它这边要补一个1加 n 分之 n 加1。那时候我们都说 n 不能等负1，为什么？如果 n 等于负1，这边就出现0，对，不行的。所以那时候我们都要求 n 要不等于负1。可是现在由于 ln 的导入，我们多了当 n 等于负1的时候也没有问题，它的结果是 ln u 的绝对值加7。好，所以我们就把它补齐了，对，拼图的最后一块补齐。有另一种解，应该不是说因为过去我们没有去讨论这个的答案，当 n 等于负1的时候，可是这次我们就把它补上来。OK， 好。So, on the other hand, we just let u is equal to f of x. So when we du over dx, u will become f prime x. So that du will become f prime x times dx. Right? So in the past, if you face 1 over u du, it will become integral 1 over f of x, right? I just replace u as f of x. Then I also replace du. I just use this to replace this one. So I can get f prime x dx. Okay, we just step by step watch the result. 1 over u du, right? So I assume u is equal to f of x, right? As I told you, u always is denoted as blah 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 x, right? It's a function of x, right? So it will be f of x. So when we just replace u with f of x, then we can try to calculate du over dx. Then based on it's a differential, so we can move dx to the right hand side. Then we can just try to replace u. 1 over u become 1 over x. Then du will become f prime x times dx. So finally, we can get this good result that this will be integral f prime x over f of x, then dx, right? As we know, the result will be taking ln, taking the absolute value u plus c, right? So the result will be ln f of x taking its absolute value plus c, right? This part will be here, right? So finally we can get this. This is a very important result. That is a very important result. Later on, I will show you an example. What is the result of LS? When we just want to integrate f from x over f of x, the result will be ln taking as the value of f of x plus c. So I will give you an example. Maybe at this moment you were a little bit confused. That okay. For example, I ask you to calculate this 2x over s squared plus minus 1 minus 5 dx, right? So based on this, did you notice that 2x upon x, s squared minus 5 f of x, right? You can see here, you can regard here just like f of x, right? So it's upon x will be 2x. So you can see here is upon x. So you can see based on this formula, you can get it will be ln taking absolute value of s squared minus 5. Then the two limits is from 0 to 2. So the result will ln 2 squared minus 5 minus ln 0 squared minus 5. So the result will be ln 1, because 4 minus 5 is negative 1, right? And this one will ln 5. So the result will be minus ln 5, right? Because this part is 0. So this is solution 1. This is the solution 1. So solution 1 is based on this formula. For solution 2, did you still remember last semester we just learned substitution rule? What is substitution? Did you still remember substitution? We try to use a simple variable to replace a complex function. So based on this, we can let u is equal to s squared minus 5, right? So next time I also teach you a tip. When you assign a simple variable u, yes, to be a complex function, right? Yes. Then what you need to do immediately? Try to du dx. Yes, correct. So then you should immediately to calculate du over dx. So that will be 2x. So du will be 2x dx. So the original one will become you can replace, you already replace u is here, right? U is equal to s squared minus 5. Then you can also see 2x ds, right? So here will be du. Then it's a definite integral, right? It's a definite integral. So from 0 to 2. So what is this? What is this? We should use 0. 0 into x for x, right? Replace with x minus 5. Then use 2 to replace x minus 5. So finally, that will be 0 square minus 5, 2 square minus 5. So finally, you will face ln u taking absolute value of x u, then minus 5 to minus 1. Then you can get ln taking as a value of negative 1 minus ln taking as a value of minus 5. Actually, this is also the same as this one, right? So there are two ways. In the beginning, if you can just find that the numerator and denominator have this relationship, f prime over x, f prime x over f of x, then you can immediately apply the rule at the corner. Okay. The other way is using the substitution rule, like that's a method you just learned. When you just replace s squared minus 5 as u, the next step for you, immediately you need to take the du over dx and try to find the relationship between du and dx. Try to replace all x with u. Okay? But actually, these two results are the same. So let me give you another example. I give you another example there. So we already learned this, right? Integral sine x ds. What's the result? What's the result?
0.
No. It's a negative cosine x plus c, right? We also learn this. What's the result? Sine x plus c. But that's the method. Did we learn this? Did we? No, we didn't learn it. Right? But right now we already have solution to this problem. Because integral tangent x can be regarded as sine x divided by cosine x. Right? dx. So did you find that if we just let f of x is cosine x, what is f prime x? Should be negative sine x, right? Right? If cosine x, we assign f of x to be cosine x, then we differentiate, we can get minus sine x. So there is sine x here, right? So we can regard this as minus f prime x, right? So please just pay attention here. Here will be f prime x over f of x. F of x, f prime x over f of x, when we just integrate it, we can get this result, right? So, but don't forget this minus, right? So it will be minus ln cosine s taken is as a value plus c. So at the same time, we can just move here to here. So the result also can be regarded as ln cosine x to the power of 1 minus 1 plus c. So it also can be regarded as ln taking second s, the absolute value of second s plus c. So either you can regard this as this one and also can be this one. Right? This is about tangent x. So we already know how to integrate sine x. We already know how to integrate cosine x. Right now is the introduction from ln x. We can also know when we calculate the integral of tangent x, we can get the result. But in the next semester, since we don't know ln x function, so we cannot do that. But right now, we already have the solution for this part, right? So I believe if I ask you calculate this, you know how to do, right? How to do? Yes, your guess is correct, but you can try to just follow this rule that this part can be regarded as cosine x over sine x, right? Through a similar way, finally you can get it will be minus ln taking cosecant x absolute value then plus c, right? So right now we already have sine, cosine, tangent, cotangent. How about secant? How about secant? Actually, secant sometimes it's quite hard to imagine it. Okay, I will show you. Integrate secant x ds. So sometimes I just think it's quite like magic. So you can regard this as secant x times 1, right? No problem, right? It's just like secant times 1 still secant x. So far, no problem. But you need to try to let this 1 become secant s plus tangent x over secant s plus tangent x. Actually, if you don't do it before, actually it's hard for you to imagine that 1 here should be converted as secant s plus tangent x over secant s plus tangent x. If you didn't do that before, I don't think you will find a way to convert 1 as this one. 如果你没有做过这个，我不相信你会知道把这一变成这个样子。天晓得这一要变成这个样子，一为什么变成不是5/5？为什么不是变成 tangent 除以 tangent？ 但是这个很神奇的地方，这神奇的一，当你做过之后，你就知道它把它变成这个样子。Why do we do that? Because if we do so, we can see, we can get that will be secant square x plus secant x tangent x, secant x plus tangent x, right? So you can see again here, if you just regard it as f of x, its denominator will be at prime x. Right? When we differentiate tangent x, we can get secant s squared, right? Try to imagine that if you differentiate tangent x, you can get this one. If you differentiate secant x, you can get secant s tangent x. Hey, you forgot the rule, right? 我们在微分 tangent x 的时候是什么 ？secant 平方 x 啊。对。我们在微分 secant x 的时候，我们得到什么 ？secant x 是 tangent x。所以你会发现分母是 f(x)， 如果指定成这个样，它的分母刚好也是 f(x)， 有没有很好 ？f(x) 除以 f(x) 的积分又来了，对不对 ？So we can get it will be ln secant x plus tangent x plus c. Right? So you can just see here we can get this one. So can you also try the similar way to deal with cosecant x? For cosecant x, yeah, for cosecant x, you can follow the same way, similar way to do that, right? You also can do that, right? So I will give you this part. You can just follow the similar rule. Using cosecant x plus tangent x. I replace 1. Okay. So finally, you can see in that semester we didn't know the integral of tangent x, the integral of cotangent x, the integral of secant x, the integral of cosecant x. We just know these two ones. We just know sine and cosine, but we didn't know the rest four ones. 好，在上学期的时候，我们只学到这里，把它缩小一下哈。上学期的时候，我们只到这里，因为什么 ？sin 跟 cosine 的微分刚好，它们两个是互相交替，对不对？所以上学期的时候你只学到这里，最后这积分这不是微分哦，对，所以你只知道这里。那这学期我们教了 ln x， 这4个就顺便补起来。好，那这4个补起来意味着你应该把它记下来。其实下学期有很多要记的，但事实上我不喜欢记了，不喜欢让它记了。不过就是说，如果你不喜欢记，起码你如果你导过一次，你就对它印象就会比较深刻了。忘了马上导，OK。So then we will talk about the last topic about this section. We will talk about the logarithmic differentiation. So you can find that when we deal with products, when we just taking its logarithm, then we will let it become addition. Why I say that? You already learned that. You can see. Okay, please just take a look at here. Look at here. See? This part is product multiplication of a and x, right? This is multiplication. After you take in the logarithm, then it will become addition. So you can see, originally the operation is product, but through taking its logarithm, then you can get addition. So similarly, if original we just ask you to calculate its quotient, then through logarithm you can get it's just subtraction 乘法变加法，除法变减法。哦，大家计算机概论或计算机结构有学过加法器跟乘法器哪一个复杂？但是乘法器比较复杂，对不对？所以经过 log 的这个函数的取值，你可以把它从乘法的运算变成加法运算，除法运算变成减法运算。但天下没有白吃的午餐了哈，你把它降下来之后，你要把它还回去的哈。出来江湖混，迟早是要还的，对不对？哦，砍人家一刀，迟早要被人家砍一刀回来，对不对？所以等一下我们再看看它转过来之后，你还要让它转回去。这个技巧用太多了，在这个 logarithm 里面哦，但是它确实是一个好方法。当你把它变成加法的时候，运算就简化很多。但是你要记得把它返回来。哦，这个在这个章节会常常牵到这个概念。Okay, so based on this idea, if y is equal to s squared plus 1 times s plus 3 to the power of 1/2 over 1s minus 1, s is larger than 1, then if I ask you, calculate this, what is this? So if you just want to follow the differential rule, it will be u over v, right? This is a u. This is a pattern of u over v, v over u. I forgot. Anyway, right? So I think if you just follow the rule, that will drive you crazy, right? Because I need to think about, okay, I need to take this part to get it square and then try to differentiate this part times this one minus differentiate this one times this one. So we have another way through the tip that, okay, so if so, it's a multiplication and this is quotient. So why not, if its original expression is just like this, we just take its ln. After you take in its ln value, then you can get, it will become ln s squared plus 1 plus ln s plus 3, because 1/2 can move down to here, right? Then minus ln s minus 1. So when you continue to differentiate it, then it will be differentiate this one, differentiate this one, and differentiate this one. When you differentiate this one, what's the result? 1 over s squared plus 1 times, don't forget, 2x, yes. Then here, 1/2, 1 over s plus 3 times 1, right? And here, s minus 1, 1 over s minus 1 times 1. So finally, it will be 2s over s squared plus 1 plus 2s plus 3, 1 minus s minus 1, 1 over s minus 1. Then, because you have to take this one, right? So this one will be, don't forget, the left-hand side will be, because y here you should regard it as blah, 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 x. So when I differentiate it, it will be 1 over y dy dx. This is very important, right? When I differentiate, you should regard it as u, right? 1 over u times du dx. So right now we can have this, right? We can continue because eventually we want to get this one, right? So dy over dx will become, if this part is a star times y. This is the result. But if you use y back and star here is blah 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 x, it's a very complex expression. However, the result is still blah 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 x times blah 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 x. Eventually, this part is all x. But maybe it's not easy for you to just explain it. It's not easy for you to explain it. Okay, this is session 2. Okay, I also list the number here for your reference. So again, let me remind you, we also will put the slides to the Moodle. And we also put the video on the YouTube. Okay? Okay, see you next week.